Okay, this video is going to start with Newton's first law. So every particle continues in a state of rest or uniform motion in a straight line unless acted on by an external force. So what this means is when the resultant force is zero, an object is at rest or moving with constant velocity. That's kind of how we're going to be using it a little bit more. As an example, so e.g., a block is pushed along a rough horizontal surface. So, trusty pen box again, so we've just got a block that's been pushed along. So if I draw a force diagram for that, then we've got this pushing force, which is causing some motion in this direction. It's a rough surface, so we've got some friction, opposing motion, and we've also got the weight of the box acting downwards and the reaction force. I think in physics you might call that normal contact force, which is absolutely fine. There's too many R's in mechanics and maths, to be honest. So we've got the reaction force, which is reacting to the weight pressing down on the board. So another thing to consider is these forces are perpendicular, and perpendicular forces have no effect on each other. Because vertically this box is at rest, then R has to equal W. So that's kind of what Newton's first law is saying. If it's moving with constant velocity, so if I'm moving it along at a constant velocity, then the pushing force, sorry, I've scrubbed my writing a bit, the pushing force is equal to the frictional force. So P equals F. If you're pushing more than the frictional force, then the box will be accelerating. You can zoom back if you need this. So it'd be accelerating if I'm pushing with a larger force than the resistive force. So if accelerating, try and make that slightly nicer. So P would be bigger than F, and if it's decelerating, then F will be bigger than P. If you imagine being in space where there's no air resistance and you push an object and let go, then that object will just keep moving with constant velocity because there's no external force acting on it. So it's that kind of idea as well. Okay, so one more example. So if we've got an object, so all our objects are really going to be modelled as particles. So objects actually have a centre of mass that they act through, but we don't find centres of mass in this course, which is a little bit of a shame. So we just model them as particles. So you don't have to worry whereabouts the weight is being acted through. So there's my particle. So yeah, I don't know if have we said this? I think we have, but maybe not. So particle doesn't have any dimensions. It's just a way to model something. So perpendicular forces have no effect on each other. So there's no movement this way. And 10 newtons of this will be cancelled with this 10 newtons here. If you wanted to draw a diagram of the resultant force, just to get an idea of what this means, then the resultant force will be 20 newtons acting upwards. So we measure force in newtons, and I will talk to you more about that next lesson, about where that unit comes from and what it means, because that fits in nicely with Newton's second law of motion, which we'll do next lesson. But if there is a resultant force, then the object in this case is accelerating upwards, and because the resultant force is constant, the acceleration will be constant. In reality, you tend to have a variable resistance force, but if you have a constant resultant force, then the object is accelerating upwards with constant acceleration. And then if you know an object is in equilibrium, then you can find unknown forces, which I'm kind of assuming is relatively obvious. But if you know that system is in equilibrium, then P will equal 30 and Q will equal 40. Remember, these perpendicular forces don't have any effect on each other. So you should have enough there to do page 158. Exercise 10A, question 6 through to question 14. But please ask each other a bit if you're not sure, you're getting stuck, because I'm sure there's someone that knows what to do. Brilliant, thank you.